Zahara, morning. Morning, everyone.
Good morning, sir.
I hope we are good. Last time we introduced, we derived the equations of inclined, of banked roads, and we saw how those equations can be looked at. I don't know whether people managed to look at some examples. The examples are not complicated if you have the right equation to use. And I told you to derive another equation. I don't know whether you people tried it out. No one inboxed me. So today I intend to finalize this area so that next week I can start with gravitation. But my girls of Nabisunsa, girls, are you there? Girls? Girls, are you there? Lugasa Fatuma, are you there? Girls, Nabisunsa girls, are you there?
Yes.
Yes. Now I wanted to make an adjustment in this lesson. How is Wednesday afternoon at 3? Girls, someone should mute. Girls, I was asking, how is Wednesday afternoon at 3 p.m.? Because this lesson is a little bit, it can always come back if we have more time, but I wanted us to use the Wednesday afternoon because gravitation, I need your attention. I need most of you attending. And Saturdays, people overmiss. So in my view, I was like, how about if we take the lesson back to weekdays? So I have a problem with the Nabisusa girls. Girls. Eh? Hello? You are saying? girls of Nabisunsa, I was asking, how about if we move this lesson to what? To Wednesday afternoon. How is it? Okay, I'll discuss with them on the group. So allow me to take you through some of these explanations. And among the explanations, we have the following. We have applications of circular motion. One includes a biker. A biker can be a cyclist, can be a border cyclist, and so on. Okay. What of Friday? Friday, Adnan. Friday, are we free at 2? The other guys of our Zoom class. Are you free on Friday?
Sir.
Yes,
yeah?
teacher. Yes.
You are always free. How about Nabisusa girls? Why are the girls not answering? That is, you are saying Friday after lunch, at 2, isn't it? Okay, guys, I wanted to show you before I can proceed today, some of the illustrations of banking. You can see this is how a bank road looks like. I think all of you can see this image.
Hey. So, excuse me, sir.
Yes, please.
Friday at 2 there's biology.
Okay.
And we have some PCB, guys.
Yeah, I knew there was something somewhere there. Okay. That's why I was opting for our lesson of Wednesday at 3:20. Okay, we shall discuss in the group. So guys, are you seeing the illustrations of what I was trying to show you last time? The derivations we are making, we are predicting when a vehicle is on such a banked road. Okay, look at these vehicles, the racing truck. This truck is moving, this car is moving on a road which is inclined. Okay, look at also this one, the same story. It's moving on a banked road. So if you're to design, you can have, for example, its normal reaction acting along that line. Then its weight is still acting vertically downwards. Okay. And in that sense, that's where the normal reaction is acting. Let me use another color. Maybe this one is not comfortable. You remember I talked about some of these things last time. So if this is the weight of the car acting downwards, then this is its normal reaction. Then you see the road, this is the line. This is the line which predicts the road. Okay? So as the car is negotiating the bend, this line is towards the center. Let me change this color. This line is to the center. Then when you resolve the normal reaction, you'll have a component of mg cos theta. Then this way you have a component of mg sin theta. Just like you've seen here. Look at this car, this one here. The normal reaction is right here. Then if you're to prolong this one backwards, you'll have the weight cos of theta. Then along the road, you'll have a component of weight sine of theta. So all these illustrations are trying to show you how a car on a banked road ideally looks like. So for those of us who are not imagining the picture very well, this is how the picture of a car on a banked road can look like in one way or the other. Okay. The same applies to an aeroplane when it is being banked. You can see in this illustration here. This is for an aeroplane which is being banked. When you look at this one here. The same applies when you go to those circuses in, but we don't have them in Uganda. Look at this circus rail. This rail can move when it is banked at one point. So all those experience circular motion. So basically, these diagrams were meant to bring out a picture more of how it looks like than what we did in the presentation last time. So if you want to see more about more of these pictures and more notes on these, go to Google and type in what? Vehicles on banked roads. Yeah. When you type in vehicles on banked roads, you'll be in position to see all these illustrations and the formulae that we have talked about. Okay, unless if someone has a question on these, otherwise we are good to go for explanations of what happens in circular motion. And among the explanations, the first explanation is going to be when a biker or cyclist, when a cyclist is negotiating a bend. He leans inwards. Now, to start with, if this is the cyclist, let me use a straight line so that you can have a straight horizontal road. This is our cyclist on the road. And this cyclist, if this is the tire, this is the body of the cycle, these are the holdings, and this is his head. So in the beginning, when this guy, there is already a friction here, but this guy has one, a component of the normal reaction, and a component of his weight. So that is before we can think of leaning inwards. So this is the normal reaction. This is the weight of the body. That is the biker and the body. Now, when the guy wants to negotiate a bend, okay, he's on the horizontal road, but he wants to negotiate a bend. For example, if this road was going this way, but it's horizontal, it's not banked, then what is he going to do? He's going to bend on this side. When he bends on this side, he's able to negotiate the bend now. Otherwise, if it doesn't bend, it is impossible. And we are going to see the reasons why. Now, before I can draw the second one, let me first talk about the reasons why this guy cannot negotiate a bend. A border cyclist cannot negotiate a bend when he's trying to. Negotiating a bend is what you call a corner, a quarter corner. The guy is trying to negotiate a turn. Now, what happens is, we have here the center of gravity, G, which is at a height of h from the ground. When you take moments about the center of gravity, you will see that you can't take moments about the center of gravity because moment about G at that about mg, moment of mg about capital G is 0 because it will be mg times 0. Then the moment about the frictional force, moment of the frictional force about the center of gravity G is going to be F times H. But it is supposed to be equal to the anti-clockwise moments, if these are the clockwise moments. The anti-clockwise moment would have been R times 0, because 0 R is not moving away from the center of gravity. So in this case, the only moment we have is FH, which is equal to 0. Now, if a body is in equilibrium or limiting equilibrium, and then it is having a moment which is equal to 0, then it is impossible for that equilibrium to exist. So it means the guy cannot negotiate a bend when he's upright comfortably and then he bends on the road. What does that mean? It means for a body to be in equilibrium, the sum of clockwise moments must be equal to sum of anti-clockwise moments. But according to this is only clockwise what? Moments. Anti-clockwise moments are 0. So if the clockwise moments were equal to the anti-clockwise moments, then the guy can negotiate comfortably the bend. Now, how does the second part play a role? The second part, once he has bent, this is what is going to happen. He's going to experience a normal reaction. He's going to experience his weight. A distance away, he's going to experience a frictional force on the ground. Now, what happens is, in this case, if this is the friction, this is going to be the normal reaction. This is going to be the center of gravity. This is going to be the weight of the body. In this situation now, we have shifted. If I may draw a line of action here, a line which is imaginary here. This red line, assume it's imaginary. Okay. Now, in this sense, what is going to happen? This was case 1. Now, at case 2, we are negotiating a bend on the road, and the guy is bending towards the center of the road. Now, as this guy bends, in case 2, this is what he has done. We want to take moments about the center of gravity. When you take moments about the center of gravity, remember we have the height here, h. We can have a distance here as small a. In this case, the frictional force will have a moment going clockwise. The reaction will have a moment going anti-clockwise. So the moment of F about G is going to be F times H, which is the sum of clockwise moments, which must be called sum of anti-clockwise moments. Now the anti-clockwise moment is going to be R times A. Now, because now we have a moment due to the clockwise moments equal to the moment due to the anti-clockwise moments, then equilibrium can be attained by this guy who is negotiating a what? A bend. Otherwise, before, if he had not bent, we would not attain equilibrium because only we have one moment, which moment was even equal to 0. So, where is the physics? Where is the science? Where is the explanation as to why the guy has to bend? The guy has to bend in order to counterbalance the moment of the normal reaction with the moment of the frictional force. This is the moment of the frictional force. Which is equal to the moment of the normal reaction. Normal reaction about the center of gravity of the body. Of the man and the bike, okay. So, in brief, what I wanted to show you, you have to show these illustrations mathematically. If the question has more than 3 marks, you have to show this and show the first part. What if he does not bend? What happens? He will not be in equilibrium. So he will not be able to be stable. Stability will be lost because the body, if it's not stable, it loses its what? Its stability. So for the guy to remain with stability, he has to ensure that he balances the moment of the frictional force with the moment of the normal reaction. So to do that, he has to bend away from the line of the normal reaction of the tires of the motorcycle. or of the bike. So in that regard, they can always ask you that question. Explain why a border cyclist bends inwards when negotiating a bend. Explain why a bicycle rider bends inwards when negotiating a bend. Explain why a motorbiker bends inwards when negotiating a bend. Those are the same explanations. I saw someone with a question. Yes, who was that? Someone had a question, raise the hand.
Teacher, why is the reaction in that position? I thought the reaction is supposed to be literally above the cyclist in normal cases, but why is it in that position?
Why is the reaction in that position? Okay. Why it is in that position? This is this is the reason. You're saying why the reaction is here, right? Are you asking why the reaction is here? Okay, Lucy. Now, remember one thing. If you have a surface which is inclined, look at my board. You see my board? If I put a phone on my board like this, the normal reaction is supposed to be perpendicular to the board. The normal reaction is always a force which is perpendicular to the surface of which the body is in contact. You know that definition of the normal reaction? That the normal reaction is always that force which a body experiences as a result of the contact of the body and the given surface. But the normal reaction has to act perpendicular to the what? To the surface. So if it acts perpendicular to the surface, this is what is going to happen. If the surface is inclined, the normal reaction is acting in this way. If the surface is horizontal, the normal reaction has to act what? Perpendicular to the surface. No matter how the body is pressed, whether the body is pressed like this, whether the body is pressed like this, the reaction starts from the point of contact vertically upwards or perpendicular to the surface in contact. So for that reason, Lucy, that is why the normal reaction is not in that line you wanted. Is that better? Yeah?
Yes, teacher, I've understood.
Okay, welcome. Thank you.
Excuse me, sir.
Yes, please.
Do you also give the illustration in the paper?
Like, hey, there's even a paper they asked you to derive. Now, first take a look at this guy. You see this guy? Oh. First take a look at this guy. Are you seeing him? He's negotiating a bend. So don't think they're just enjoying. You see the border riders, for them, they think they're enjoying. It is the physics laws they are abiding by. They have to abide by the law. If they don't, they fall down. Why? I have given you the reason. The moment of the frictional force on the road will not be counterbalanced. So what will happen? It will pull them down so that they can get stability on the ground. Okay? So I was trying to show you some of these illustrations. I think it has stopped to share. I expected it to move, but it's not moving. So with that reason, you're going to meet the write-up in the notes. So in case you're explaining why, it's because I've said the moment of the normal reaction is to be counterbalanced by the moment of the frictional force if the guy bends inwards. If he doesn't bend, the moment of the frictional force is not counterbalanced, so the guy will lose stability and will fall off the what? Will fall off the bike. So you'll come to your notes here. The notes are here, and you'll see what the notes are saying. Of course, what I've just showed you is right here. Now, sometimes they go ahead and ask you to find the value of mu. Now, do you see this part where the guy is? If you extract out this part, it forms a right angled what? Triangle. With this as 90, with this distance as A, with this one as H, with this one as alpha. So that tan alpha can be got from H over what? From H over A. Whereas also tan of the, because the vertical force there is the normal reaction, the horizontal force is the frictional force. Therefore, tan alpha also is the same as a normal reaction out of friction, which is supposed to be equal to H over A. And it is from here that you can say R over mu R is equal to H over A. And with this, you can get mu from A out of H. If they ask you to find the coefficient of friction. Or you can also say mu can be equal to 1 out of tan of alpha. So all these ones can be talked about or can be asked to be derived. Around 3-4 years back, that number came in UNEB, question 1, and they asked you to derive. After deriving, they asked us to explain. It had around 7 marks. That was strange. Then the second question, which can be said, these ones are some of the questions which are there, which are concerning vehicles on banked roads. I told you the numbers are very easy. You just substitute and get the answer. Okay. The other bit also is that, which I've missed in explaining this. Remember, I told you, if you're to look at, if you're looking at this diagram, the friction acts towards the center. So it provides the centripetal force. So since friction provides the centripetal force, it will be equal to mv squared over what? Over r. So in case one also wants to get the value of the speed with which one has to negotiate the bend, then you would realize that from tan alpha is equal to r, I can divide over mv squared over the radius of the circular path. But this is also the same as h over small a. You realize that you have RA is equal to h times mv squared over r. But also recall in this formula, which we have derived earlier using moments, we had the r times a, as equal to f times what? F times h. And with that, still, if you substitute their friction as a force, you would still get the same result come up. So therefore, no need of worry that in case they asked you, what if the value, what if they said derive this, find the velocity with which the person has to negotiate the bend. Yeah. So you would find that you can still get that answer for someone to negotiate a bend using velocity as I've derived here. So you can see that from here, v squared is equal to r a times the radius of the circular path divided by m times the height of the center of gravity from the ground. Okay. So with that, you can have all the derivations required in this illustration. Our friend who normally does research for us, you can do more research on this and also send us that presentation. Any other questions? So if no further question, there's another common question which is pardon? Oh, actually here, when you get this v, it's going to be the root of. So the speed for one to negotiate a bend should be less than or equal to if you increase the speed, you are going to go down terribly. That's why the border riders, when they reach a corner, they reduce the speed. They don't want to exceed this speed. Yeah. Then 2, they also reduce the radius of the circular path. If the whole of this is the road, it is safer for them to pass here than passing this way because they will be increasing the radius from the center. And when they increase the radius from the center, they will be prompted to increase the speed, right? Then another thing is they should reduce the height of the center of gravity. You remember if he was standing, the center of gravity, for example, was here. When he changed the direction, the center of gravity changes. It is lowered. So they have to always lower the center of gravity by reducing the value of h. So they can ask you for those conditions. Just like in the other bank road, they could ask you conditions for car to skid, to slip, overturn. Here they can also ask you the conditions for the rider to fall off the bike. What is he supposed to take into account as precautions if he doesn't want to fall off? Okay. Someone was saying something before I can go to another explanation.
Teacher?
Yes, please.
My question is, would you please give us an example of a question that can come and they need efficiency of friction?
When they need the coefficient of friction.
Yes.
In this case, the examples which come around this area, this is just, they just ask you to do the derivation and then to explain, and then also to give the conditions for the guy to negotiate the bend. Those are the common areas we said about this part. Okay.
Okay.
Then the other thing which I wanted also to talk about, they can ask you to explain why. They can ask you to explain why a car moves faster on a banked road than on an unbanked road. Have you seen those racing cars? The images I showed you earlier. Those racing cars, those images I showed you earlier, those cars run terribly fast when they are on that incline, more than when they are on a horizontal road. The reasons we are going to see them. This is what I was trying to say. When we are here on this banked road, the cars are terribly running fast on this incline. Whereas when they are on a horizontal road, you see this part here? That is a bend. After turning this bend, you see the circular path? This is where the circular path is tending to be estimated. So we estimate that is the center as it makes the turn. But after this turn, if it is proceeding this way, it comes to a horizontal road. Okay? So when it comes back to a horizontal road, the speed what? Is not as fast as it was before when it was on an incline. Now a question can be said, explain why it is so. Right? You see this one, it is a little bit in front of these two. This one, this black one, is in front of the other two silver cars because it is more on an incline. Look at this one where he is on this other car. You see this one. Where is it? I think it has gone out. But now I need to do the explanation because people have a meeting in Abisunsa and I have to finalize before the meeting comes to start. Now, when they ask you, explain why vehicles attain maximum speed on a banked road than horizontal roads. Sometimes they say, why is the car faster on a banked road than on a horizontal road? The explanations are the same. Now, to start with, on a horizontal road, this is what happens. When you're on a horizontal road, these are the conditions we have for the car. The car has its tires in contact with the ground. It has a normal reaction. I'm assuming this normal reaction R is the total reaction on the both tires. Then the car has its weight, which is what? mg. Then the car has the frictional force. But the car on a horizontal road, as it turns to the center, the frictional force is what provides the centripetal force. So the frictional force the centripetal force is provided by only a component of the frictional force. Now let us see what if it is inclined. If it is inclined, when it is inclined, this is what is going to happen. We shall have a car here, as we have seen back there. Then we shall have a normal reaction. We shall have the weight of the car. Then we shall have a component, which is mg cos theta. This is theta. Then we shall have our mg sine theta. Then we shall also have a frictional force here. Now, remember, this is the line towards the center. I think those images have showed you clearly. That is where the center is. That's where we have centripetal force. Now, you will see that the centripetal force, which is mv squared over r, is going to come as a result of these. One, here there is cos theta. There is theta. So when you resolve r towards the center, it will be r sine theta. Then resolve friction. When you look at this friction subtends an angle of theta to the horizontal. So when you resolve friction horizontally, you will get F cos of what? Theta. So the centripetal force is provided by R sine theta plus F cos of what? Theta. Now, that is where the explanation is. That is why sometimes some of these physics concepts, you need to know the equations, the derivation, where it comes from. You don't just jump into explaining. Just like someone was asking me earlier about why a satellite may burn. You don't just jump into saying a satellite may burn. You have to talk about the equations, show exactly what is happening, show us the variations when R increases and the like. Now here, they're asking you, why is the car running faster? In the first case, we had mv squared over r is equal to f. You see that v squared is equal to f times r over m. But in the second case, we are having mv squared over r is equal to r sine theta plus f cos theta. Do you see in this case that v squared is equal to r sine theta plus f cos theta times r over m? Now, this is how the explanation goes. In case one, when the road is not banked, the component of the frictional force is what provides us with the centripetal force. It is what predicts the speed, okay? But that speed is not so much as compared to the second speed. Why? Because in the second case, the component of the centripetal force is provided by both a component of the normal reaction and a component of the frictional force. So what does it recall for? It calls for a higher velocity on a banked road than on an unbanked road. It is the same explanation as to why when a person is driving a car, they can run terribly very fast on a hill. They can step on the accelerator when they're ascending upwards. But when they're coming back down, my friend, the force driving them down is the force due to the engine power plus mg sine theta, only overcoming friction. But when it is climbing up, it has to overcome all those conditions. So it drags a little. The drag is much when it is climbing up. But when it's coming down, there is a drag pulling it down. And then there's power of the engine, which also gives a force. Hence, the car runs faster when coming down an incline than when going up an incline. So when going up an incline, you step on the accelerator as much as you want. Now, even here in banked roads, you can step on the accelerator on a banked road. Comfortably, the car will go without overturning, without slipping. But if some of you have ever driven cars, if you drive on a horizontal road at a terrible speed, the car starts shaking. You start experiencing turbulence. You start experiencing Bernoulli's principle as the car wants to fly off. Why? Because the airwaves will be running very fast on top of the car and the airwaves down will be running at a very slow speed. Hence, the forces of the molecules down tend to lift the car up. So to avoid that risk, you accelerate or you step on the accelerator when on a banked road, that condition will not be experienced. Why? Because we have a component of the normal reaction and a component of the frictional force other than on the horizontal road. Those explanations, both of them, you have them in the notes. But unless someone has not understood the explanation I've given, I can now respond to some of your queries. Someone was saying, teacher, pardon the explanation. Where exactly? Kaira? Kaira?
It's okay.
I've understood. Any other concern?
To understand.
So now, guys, if there is any other concern, we are done with circular motion. Those who have missed, they should not come for gravitation. Eh? Honestly, if you have not covered this, don't come for gravitation. But those are your problems. Yeah? So my girls of Navisunsa, I was requesting if we could move the lesson to Wednesday afternoon at 3:20. Then we merge that class with the normal Zoom class I have. It would be better. And there people, I think, don't over miss. Here, people are still sleeping, I think. But still, it is your concern. If you miss, those are your problems. Then my boys I deal with on the Wednesday, I trust by Wednesday. Since we have finished heat, I will convert this lesson and use it for gravitation physics. And then we see how we can speed up our mechanics. But please, I need you in the beginning of gravitation. Whoever intends to attend, there are those first laws of Kepler. You can read about them. They play a very big role in the entire topic. You don't understand them, it will be a very big challenge for you to pick up. So please tell your friends, I'm starting a new topic. Come Wednesday 3:20. In case some people are not willing, or in case the Navisunsa girls can't make it, please let me know. But I trust all of you can make it, so that we can have that lesson during the week. But I want everyone to attend the beginning. You don't attend the beginning, you can't understand the later bit. Okay? Any other further questions concerning these illustrations, please inbox me, and also visit Mr. Google for more assistance and more illustrations. So meaning Saturday lessons is no more over. Tentatively, no more, unless we miss a lesson and we want to compensate. Because I'm seeing it is disturbing you, even me. I have functions, I have my farm. So right now, I'm going to the garden, but I've parked close to someone's garden and I'm teaching from there. So, but it's okay. I was okay with it, but it's just that Saturdays, weekends, we are over-engaged. Let us leave the weekend so that we can always just borrow more time in case we have missed some time. All right? Kale, if no other questions, please have a nice weekend and have a good day.
Thank you, teacher.
Anytime.